Worms locomote using a system of peristalsis, or peristaltic motion. This means that sections of their body expand and contract to push themselves along. There have been quite a few research projects for robots that move like this, and I previously built my own simple version which used 4 concertina mechanisms driven by servos to make 4 expanding and contracting sections. This didn't work very well because as each section expands and contracts, it also gets longer and shorter, which pulls or pushes the other sections in and out either side. So with all the sections doing this, getting it to be synchronised efficiently was quite difficult. Worms have little bristly hairs on them which act a bit like a ratchet to help them go forwards and not slip backwards, so ratchet wheels would probably have helped on my mechanical worm. But this time we're going to try and make a more efficient design without putting wheels on it. The plan is to keep the concertina parts but make them slide independently of each other so they don't push and pull the sections either side. Let's get the parts 3D printed and assembled and it'll be clearer how it's going to work. We need to make 4 sections for the worm, so we've got lots of duplicate pieces to make, but here's just a few of them. There's some levers to make the concertina and various other parts to link the sections together. Just a quick ad from my 3D printing sponsor, thanks to LolsBot 3D printers for supporting my channel with 3D printers. It makes it much easier to have lots of printers that I can print all the parts in parallel. And thanks to 3D Fuel for the filament for this project, all these parts are printed in Pro PLA+. I'm going to use these V-wheels and V-slot aluminium extrusion to make the sliders for this project. Normally you need more than one wheel though. Both ends of my concertina are going to slide up and down and each one has 4 wheels so that it doesn't skew and jam. You can see that we've got the wheels inside there, those are supported on bolts, and then my aluminium extrusion is 2040 extrusion and that slides in there just fine. So we've got these end stops as well, which are also the joints between the sections of the worm, and both ends of that can slide. The concertina part of this is really similar to last time. It's a kind of trellis thing with just some normal joints that get shorter and fatter as it moves. And of course that fits onto the 2 sliding sections, which allows either end to move and the whole thing to slide up and down. So unlike the previous worm, which was just this concertina piece, and it meant when it got shorter and fatter, this segment got shorter and it pulled the other segments in as well, we've now got these fixed ends that always stay the same length. The other thing we can do is pull this up and then slide this piece along here, bring this down again, bring it up again and slide it along. So it should give us a much better locomotion. So we just need to put some motors on there now. I'm planning to use servos, but let's hope they're powerful enough to operate those segments. I'm using 20 kg torque metal gear servos that I've used in a lot of projects, and they come with these brackets for building robots, and those are pretty powerful. One of those concertinas the whole thing up, and one drives it the whole length of that sliding rail. So that should give us every combination of motion that we need to make it locomote. I'm using an Arduino Mega here, and I've got a 7.4 volt 2S LiPo to just power those servos directly, so that should all be just fine. So I've just got a very simple set of timers, and I'm using the servo library on the Arduino to drive those servos to the position. So it does go along, but the only reason that really works is because it gets overbalanced, and that's because the servos are moving at full speed to the position that I'm telling them to on fixed timers, so it's kind of jerking around a lot. What we really want is a much slower motion, and we need them to move over a much longer timescale so that we get a much smoother motion. To do that, we're going to use the Arduino ramp library, which is really useful, and that allows us to specify a step input change, and it will interpolate between the positions, so you can see the blue line is the step input change and the red line is our output. If we use that to drive the servo, instead of it moving as fast as it can to get there, it will slowly change over time, and we can specify the new position and the time we want to interpolate over. I fitted an enable switch on which starts all the timers, so now we can see with that ramp library running, driving the servos, we've got a lovely smooth motion. So you can see the whole thing expanding, contracting at one end, driving the spine down, expanding again, contracting again, and repeating it. But it's moving much smoother than it was. Each action out of the 3 actions here takes 1 second, so it's a 3-second cycle, interpolating with that library, with each being a 1-second move. It's not getting anywhere though, and that's because it needs the other sections to push it along. But luckily I've been making 4 of these as we've been doing the whole thing, so I've got all 4 sections to stick together for the worm. But before we see how well that works all together, it's time for a quick ad from the video's sponsor, which is PCBWay. PCBWay is a one-stop shop for PCB manufacturing, assembly and other types of manufacturing services all under the same roof. PCBWay manufactures all sorts of boards, including standard fiberglass boards, but also aluminium PCBs, flexible PCBs, and rigid flex PCBs, which are part rigid and part flexible.
PCBWay also provides CNC services including online CNC machining, sheet metal fabrication, 3D printing and injection moulding. Their CNC machining services include a wide range of materials, including aluminium, stainless steel and various plastics. If you don't see the material you'd like, you can also choose from custom materials. PCBWay's 3D printing services include SLS, SLA, DLP, FDM and more in a variety of materials. Check out the PCBWay website to browse for a variety of finishes and get a quote. Check out the PCBWay shared projects section. This is a community of user-submitted projects with PCB schematics and parts listings, so you can reproduce the projects you see there. They also have a module store which has all sorts of items for sale, such as Arduino boards, toolkits, robot parts and kits, and sensor modules. Find out more now at PCBWay.com, and I'll put that link in the description to this video. Right, let's power up this robot worm.
These have got ball joints on each end, which is just basically a ball and a cup for it to fit into, and I'm going to bungee those together so they can move all around. I just tied some bungee cord on there, looped it around a few times and tied a knot. So obviously with two sections doing the same thing we don't get very far. We do get a little bit of motion, but that's just because that spine has some inertia because of the metal and it just pushes it forward as it moves a little bit. But really what we need to do is adjust the sync so that one pushes forward and the other one pushes backwards as it goes. So let's try two sections which are out of sync. One is getting triggered 1500 milliseconds, that's a second and a half after the other one, and as the cycle takes 3 seconds for each of them, one is basically 180 degrees out of phase if you like. They're not quite doing what they should, but it's certainly locomoting along. Here's all 4 sections linked together. They're still a second and a half behind each other as we go from the front to the back, and since each section is on a 3-second cycle, that means that the first and third sections are in sync with each other, and so are the second and fourth sections. This seems to be quite effective, because it means that it's actually lifting off the ground in the middle. We've got 2 sections pushing the spine forward, while the other sections are pushing it backwards. And you can actually see those sections lifting clear off the ground because they're supported by the other sections either side when they get thinner. As they get fatter they push back, and since some sections are off the ground that's much more friction, so they virtually don't slip at all. You can see they're pretty much stuck in place as they push backwards. It's quite a satisfying motion to watch, and these rollers on the bottom are actually fixed. They're not rolling around at all. You can see some of them have got 2 screws in, and they also don't have any grips on, they're just smooth 3D prints. So I'm pretty happy with the way this locomotes with virtually no slippage. I tried messing around with the timing here, so basically now we've decreased the sync to 1 second. That means the second section back is 1 second behind the first one, the third one is 1 second behind the second one, and the last one right on the tail is 1 second behind the third one. But this doesn't seem to work at all really, it's virtually getting nowhere. So then I tried decreasing that to 500 milliseconds, but of course we're actually getting closer to them all doing the same thing at the same time, so that means they're fighting each other instead of basically helping each other, with some pushing back and some being thinner and going forward at that time. So this really doesn't work at all, and it really doesn't locomote well. So then I thought I'd go the other way and I increased it to 2 seconds. Remember we had a second and a half when it was working really well, and yeah, this is just as bad basically. It kind of is going forward, but I really think the best kind of thing to do here is have 2 and 2 in sync with each other, some pushing and some pulling. So obviously when they're fatter, they're pushing the whole thing back, and the thinner ones can lift off the ground and go forward at that time, and that just seems to be the most obvious answer and the best way to sync the whole thing up. So I'm pretty happy with that. Obviously the front and back segments are dragging on the ground because they're not supported by sections either side, but they still don't have that much friction because they are getting thinner, and of course we've got 2 sections at that point actually pushing back which are fatter, so that doesn't really seem to make any difference. There's hardly any load on it and the floor's smooth, so everything works fine. I'd really like to make a much bigger version that I can ride on like some of my other weird vehicles. It would be pretty cool to take to events. That means building each section about as big as a bicycle though, which means there would be quite a lot of friction on the front and back sections as they're unsupported and try to push forward. One option is building a kind of suspension bridge that holds the back and front sections up, and that could also be used to make it steer by having cables that pull down the sides so it bends as it goes. I have considered that the expanding and contracting concertina parts aren't actually that efficient, so maybe we could just have some sort of foot that moves up and down and slides back and forth, or even multiple feet on sliders next to each other in each section. That's not quite as much fun to look at though, so I'll probably stick with something that looks like Peristalsis.